in this experimental setup, my dear kids, we have two masses. The first mass is of around 870 grams and the second mass is of 1.356 kilograms. So here you can see the second one is much heavier as compared to the first one. So here, if I put the smaller mass like this on the surface and if I allow the heavier one to hang from the other end of the surface. Now the surface is quite smooth over here. So as you can guess, the second one being heavier will pull the first mass on the surface like this. Why? Because there is a tension in the rope and that tension force will do some work. How? You see that? It will move the smaller block from point A to the point B like this, right? But if I make some small changes in this experimental setup, the value of work done will change for the same value of displacement. Let's have a look at the second, experimental setup and see how the effect changes, Now again, we have the same two masses of 870 and 1.356 kilograms. And I'm putting them again in the same way. But right now, the difference is here we have introduced a pulley at a much higher level. So you see that instead of simply keeping the rope on the same level, I'll just keep the rope at an angle. And now you see that again, if I release the heavier mass, it will start falling and it will again pull the block from the point A to point B. But in this situation, the value of work done will be different. Why? Because in the first case, when the tension force was acting along this way, the value of force that was doing the work was different. And here, when the force is acting over this particular pulley, so right now you see that the value of tension force that is performing this displacement has been changed, right? And now we can observe many things like this in this particular video. So let's have a look at that and understand all these concepts in detail. Alright, so hello and welcome everybody on your favorite platform Physics Wala. This is your physics mentor Gaurav Tiwari, and today my dear kids, we'll be learning the concepts of work, energy and power. My dear kids, we'll be starting this chapter with the concept of work. We will talk about the work done by constant and variable forces both. After that, we will be discussing the concept of energy, where we will talk about types of energy and the work energy theorem as well. And after that, we will talk about the concept of power. My dear kids, after this explanation, you will find that you are absolutely clear about the numerical as well as the theoretical understanding with lots of interesting demonstrations. My dear kids, after this class, you will also get a free DPP that you can access on the app through the link given in the description. So if you do both the combination, if you just go through this lecture and also solve every question of the DPP, this chapter, you can get 100 out of 100 in every single exam. I mean, if you get two questions in the paper from this chapter, you will attempt both of them with 100% accuracy. That is my promise to you, right? On that note, let us start right away this particular chapter and ace it. Alright, so before starting this particular chapter, let's go ahead and move on to the NTA website and see what is the syllabus of this topic written on the NTA website. So here you can see that this is the syllabus of work, energy and power. And we can write down all the topics in a better way, in a clear way, in a step-by-step manner in this format like this. So you see that every topic written in this format, right, like this. You can also write in point-wise manner. So now, if you want to divide every topic, you can have three little sections out of it. Now, the first section is most important. So the concept of work, power and energy. So you see that, right? Yeah, till here. Or we can say till here, right? So we can say that from work done by constant force, work done by variable force, kinetic and potential energy, work energy theorem, power, potential energy of the spring, conservation. So all of those, and then conservative and non-conservative forces. This is the part number 1, right? And most of the numericals and most of the problems are asked from this part itself. So around 90% of the time you will find the problems are asked from this part. So we'll be investing most of our time in the first section. Now, in the second section, you can say that motion in a vertical circle, and at last you have elastic and inelastic collision. So, in NEET, for the JEE, this topic is important, but for the NEET exam, I have seen they don't ask many problems from this particular section. So, when we are going to design this class, we'll be allocating most of the time for the section 1, then for the section 2, and then at last for the section 3. This is how we are going to structure the available time ahead of us, right? So let's move ahead and talk about the first part first, right? And we will be starting our journey with the concept of work done, right? So here you have it, work done by the constant force. So now you know that what is a constant force? A force that does not changes its value during the displacement of the body, right? So here you have a box and a force is acting at an angle theta from the horizontal, right? And the box is displacing from here to here. So you know that what will be the value of work done? In the vector format, the value of work done will be force dot displacement, dot product of force vector and displacement vector. Now, since work done is a dot product of these two vectors, work done itself is a scalar quantity. We know that, right? And if you want to write down in a grade 9th format, you can just open it up and the magnitude will be magnitude of force, magnitude of displacement into cos of angle between them. So I guess that part is very self-explanatory, and we can move ahead and talk about this part. Look at the angle theta over here. You see that if the angle theta is more than 90 degree, if angle theta is less than 90 degree, so cos theta will be a positive number, right? If cos theta is a positive number, so work done will be positive, right? So here you see that as long as this theta is less than 90, so work done will be positive, right? So in visually, how can you see that and talk about the positive work? How does the positive work looks like? So you see that here, if a box is here, think about it, and a force is acting like this. So see, as long as the angle is less than 90 degree, the nature of the force is to push the body along the displacement, right? Okay. But if the angle becomes more than 90, so what will happen? The displacement was happening in this direction initially, and now the force is acting at an angle more than 90. So you see that this force does not want to push the body in the direction of displacement. Rather, it wants to slow down the body or in that direction, or it wants to move the body in the opposite direction of the displacement. And in that case, what happens when the angle theta is more than 90 degree, you see that it does not want to contribute towards the direction of displacement, and hence it causes a negative work, right? It causes a negative work. So positive work, all these examples are there for the positive work when you're lifting a body and when the spring is, pushing in one direction, right? So here it is. So now negative work, you can say that negative work. So when the body is moving forward, the friction is doing the negative work. Why so? You see that the body is moving forward, the friction is acting in the backward direction on the body, right? So friction, for the angle for the friction, what is the angle right now? We can say displacement is this way, friction is acting this way. So friction is making an angle of 180, right? You see that? This is the body, it is moving in this direction, so it is covering a displacement in this direction. This is the direction of displacement, right? But the angle of friction is acting in this direction, and the angle between friction force and the displacement vector is 180 degrees, so more than 90 degrees. So clearly friction is not contributing in the direction of displacement. So basically friction is doing the negative work over here, right? I believe the idea is very, very clear. Now let's move ahead and talk about the other ideas as well. So these are the examples of positive work, and here we have zero work going on. So zero work is there when the force is zero, or when we are not getting displacement. So if you push the wall will not get any a change in its position, so the displacement of the wall will be zero, and in this case we'll be getting zero work. Or you can clearly say that work done is force dot displacement, or FD cos theta. So looking at all three parameters, we can get zero work. When the force is zero, we zero work. When the displacement is zero, again zero work. And when the theta has a specific values, a specific set of values, be it 90 or its derivatives, so the value of work done will be zero, right? Now the examples of zero work, here you see that a satellite is moving around the earth, right? So what will happen? The centripetal force on the satellite is acting toward the center, right? You know that if a body is moving on a circular path like this, so what will happen? A force is acting on the body towards the center, right? And if that force is acting towards the center on the body, what will happen? You see that displacement is, this is the direction of velocity, so displacement wants to happen in this direction. At this instant, the direction of the velocity is like this, right? And the force is like this. So what will be the value of work done by this force in this direction, in this displacement? We can say that the angle between the force and the displacement is 90 degree. So this force is not performing any work, right? So work done by this particular force is zero. So my dear kids, we will learn that if a force is not contributing in a certain direction, it cannot make the body faster or slower. So the satellite will continue to move with the same speed around this earth, right? So we will look at that when we will understand the work energy theorem in a while, right? So this is the concept of work done in this situation. So here it is. Now it is possible, my dear kids, that the force acting on the body is variable by nature. For example, we can also have a spring like this, right? And now what is happening, when I try to extend the spring, I extended it by a small amount, and for that I invested some force, right? But let's say I was extending it for 5 centimeters, and to extend the first 5 centimeters, I had to invest a force of, let's say, 20 newtons. Then again I have to extend the spring by the same amount. Again I have to extend by 5 centimeters. But then I realized this time I did not invested the same amount of force, right? Previously I invested, let's say, any amount of force. Let's say that this is the spring. I extended the spring by 5 centimeters, and for that I invested 20 newtons, right? And now again I extended the spring for some same amount, 5 centimeters again, but this time I realized I had to invest much higher force because it is harder to extend it further. Now when I have to extend it again for the same amount, I have to apply even more force. Again, when I have to extend by the same amount again, I have to apply a lot more force than the previous 3 cases, right? You see that the value of force you are supposed to be needing, the value of force you need to apply for the same displacement does not remain same, right? With every increment in the displacement, as soon as the displacement is increasing, the required force to deform it further is increasing even further, right? So you see that what is happening in this situation, the need of force, or you say the value of force, increases if you are increasing the displacement, right? So these kind of situations give a different scenario, right? And that scenario is called as variable force, right? So here the spring force is an example of variable force. Clearly, I believe the idea is very, very clear, and it's a very general case. This is not the spring force, it's any random situation when the force is simply changing with time, right? Now when the force is changing with time, how will you calculate the value of work done, my dear kids? So far, when the force was constant, you said the value of work done will be F d cos theta. So here in this formula, you can only put one value of force. If the force is variable and it is changing its value, how can you put the different values over here? You cannot do so, and hence you cannot use this formula when the force is variable, right? In those situations, my dear kids, we'll be using this particular part, right, where we'll be using basic integration, and in that case we can calculate the value of work done. So here what will happen? The value of work done will be from here. Let's say that the body is displacing from an initial position, right? This force is displacing the body from the initial position xi to the final position xf, and during this journey we want to calculate the value of work done. So what will happen? Just mark this portion first and calculate area under the curve in this specific segment wherein you want to calculate the work done, right? So you see that if a body is displacing, if a variable force is displacing the body from initial position to the final position, how will you calculate the work done? If a constant force is displacing from initial to final, you can simply multiply the constant force with displacement and cos of angle between them, you can get the value of work done. If a variable force is displacing from initial to final position, how will you get the value of work done? By integrating it or by taking the area under the curve between these 2 points, right? So if you integrate it, integrate the force fx dx, so initial position to final position, and that's how you get the value of work done. Let's sum it up. My dear kids, if a constant force is doing the work, then the value of work done will be simply f d cos theta, or simply f vector dot d vector if it is written in vector format. But if the force is changing with time and the body is displacing from the initial position to the final position xi to xf, how will you calculate the work done by variable force? So by simply integrating xi to xf fx dx, right? So I believe the idea is very, very clear, right? Now in this diagram you have both the situations, positive work and negative work. You see that here the force is in the positive direction and the displacement is also in the positive direction in this part, right? That means force is supporting the displacement, right? In the part below it, you see that the force is negative. That means if the displacement was happening this way, the force is acting the opposite way. And if the force is opposite to the displacement, that will perform the negative work over here, right? So yeah, this is it. Now the next thing is the spring force. As you have seen already, that the spring force is an example of a variable force, and the nature of this force is such that as you are incrementing, in an incremental way, you are increasing the displacement of the body, the required force increases, in the same proportion, right? So here it is. This is the body, this is the external force, and what is happening as you displace it, what will happen? The displacement is further increasing. So what will happen? The required force increases as well, right? So if you are, let's say you are calling this, you can call this displacement, or you can also call it deformation of the spring, right? So here you have it. Here you have it. So I can call it, let's say this is the spring. Initially the displacement is 0. If I connect the block over here, a mass over here, the displacement of the mass initially is 0. And now if I displace it for 5 centimeter, so I can call it that displacement is 5 centimeter or the deformation in the spring is 5 centimeter. These terms are interchangeable in the question, right? So yeah, so no worries about that, right? So what will happen? So we can say that the required force or the restoring force or anything is proportional to the displacement. But there is one more interesting view out of it. So what is that? If you are if the displacement is happening in this direction, you know, you can experience the restoring force in the spring is acting in the backward direction, right? So the spring is applying the force in the opposite direction. So if you are causing the displacement in the forward direction, the spring will apply the force in the opposite direction. So this is the force applied by the spring, Fs. You see that when I am extending the spring, what will happen? When I am extending the spring, what will happen? The spring will try to pull me back, right? And with how much force it will pull me back, how much force will be applied by the spring, it depends on how much extension I have provided, right? If I extend it further, the restoring force applied by the spring will be much higher. So this is how it is, but the direction of them is opposite. So Fs is proportional to x, but with a negative sign. This negative sign tells us that the spring force, the direction of the spring force is opposite to the direction of displacement. I believe the idea is very, very clear, right? So over here, you can remove the proportionality sign and a constant will come into the picture. That is a spring constant. So that will give us an idea that the force applied by the spring on the object is minus kx. The minus sign is telling you that the spring force has a direction opposite to the displacement or the deformation caused. All right. So this is it. And if you have to calculate the value of work done by the spring force, clearly you can say that spring force is a variable force, right? More you deform, more forces you get, right? So work done by variable forces, integral of fx dx. So you just integrate that and get the value of work done. So integrate the value of work force over here. So force is kx minus kx, or you just integrate it from the initial position to the final position. Initial position, let's say particle had 0 displacement initially and finally it had xm. So just integrate it from 0 to xm. So integration of kx is kx square by 2. Right, kx square by 2, just put the limits and this is the value of work done. I believe the idea is very, very clear, my dear kids. Let's move on and talk about this idea. Here you have the gravity. What will be the work done by the gravity? So you see that in one way, gravitational forces are also not a constant force, but because the value of g changes as you move higher, right? You have understood in grade 9th that the value of gravitational constant does not remain same with height, right? But for reasonable heights, and for significant height, I would say, right, in day-to-day life that we can experience, you can throw a ball up to how many? Like, let's say 50 meters, 60 meters, 70 meters, 100 meters, if you are so powerful, right? So for those kind of distances, the variation in the value of g is negligible, right? So if the motion is happening closer to the surface of Earth, we can say that the value of gravitational forces will not change significantly, right? So in that case, we can say the gravitational force can be treated as a constant force if the motion is happening closer to the surface of Earth. If motion is further away, so the value of g will change and it will now experience a different value of gravitational force, right? So for now, what is happening? Here, the person is lifting the body against the gravitational forces. So how much work he had to do against the gravitational forces? So this is how much work he has to do. So because the body he is lifting against mg, so mg, and he is lifting for the height h, and the angle between the displacement and the force is 180, right? The gravitational force is acting downward and the displacement is up, so angle is 180. So this is how much work was invested, right? minus mgh. I believe the idea is very, very clear. The negative sign is just showing you that, the gravitational force, mg is opposite to the displacement, is acting in the opposite direction to the displacement, right? So this is why we have negative sign. This is the work done by gravity. All right. Okay. Here the body is falling. So you can say that both the theta is going to be 0 and theta is 0. So cos 0 is 1. So work done will be mgh, positive work. Here you can say that the force of gravity is supporting the displacement. All right. Work done by variable forces we have calculated already. So here we have it. A force of that many Newton acts on a body of 5 kilograms and it displaces it from this point to another point. What will the value of work done? Let's solve multiple questions, right? Most of the questions I will solve, but if the calculation become very tedious, so I will just explain you how to calculate it. So that part you can do as well without a problem, right? So here you have it. The value of force acting on the body is this. How much force is acting on the body? 10 I cap minus 3j cap plus 6k cap, right? It is acting on a body of mass 5 kilogram and it is displacing it from this point to this point. You see that initial point of the body was 6 I cap plus 5j cap minus 3k cap. Final point of the body was 10 I cap minus 2j cap plus 7k cap, right? So what will be the displacement vector, right? If a body is moving, this is the first point, right? Has a position vector r1, right? In the vectors you have understood this part, right? We have another point with the position vector r2, okay? So what will be the displacement vector? The body is moving from point A to point B. So we need to talk about this vector, right? Displacement vector. So what will be that? We can say displacement vector in this situation will be r2 minus r1. So just subtract it. 10 minus 6 is 4. Minus 2 minus 5 is minus 7j. And 7, this minus this. So 7 minus 3, right? So it is plus, so that is 10k, right? So yeah, now you have the displacement vector and now you have the force vector. You can just multiply them and get the value of work done. So what will the value of work done? Value of work done will be force vector dot displacement vector, right? So force vector is this 10I minus 3j plus 6k dot displacement vector. So 4I minus 7j plus 10k. So what will happen? You know that the same dot product becomes 1 and of anything else becomes 0. So you just have to multiply the coefficient, multiply this by this, and then 10 by with the 3 by 7 and 6 by 4, 10, and just add it up. So I believe the idea is very, very clear, right? Okay. So this is the same thing that we have done over here. Just displacement vector is this 4I 7j 10k, right? And the work will be the dot product of these two things. So force vector is given, this is given. Multiply that. 4 into 10 is 40. So 40 is written over here. 7 into 3 is 21. 21 is written over here. Minus will become positive. And 10 into 6 will become 60. So 60 is written over here. I believe the idea is very, very clear. And you just multiply it and you'll get the answer over here, right? So I hope everything is good. Now let's move ahead and talk about the next part. Okay, so over here we have another question. A particle is moved from 0, 0 to AA under a force this much, right? So particle is moving from 0, 0 to AA under a certain force, right? Now there are two paths. Path A, so we are moving the body from point O to P along two paths. First of all, you can take the body like this and you can also take it like this, right? So the end result is same. Particle is moving from O to P. So first of all, it is moving from path 1 and then it is moving from path 2, right? We need to know that if the path 1 has a work W1, right, and if you move it along the second path, the total work is W2, total work along this path is W2, what will be the relation between both the work done, W1 and W2? So let's think about the work done in the first path. Work done in the first path is F dot D. So force vector over here is 3I plus 4J. displacement vector from here to here, it's ai minus ai plus aj. ai plus aj. So simply this point is 0, 0, so doesn't matter. So here you just multiply it, 3a plus 4a or 7a. This is the value of work done along the first path. What will be the value of work done around the second path? So from here to here plus here to here, right? So work done from O to Q plus work done from Q to P. So from here to here it will be force vector is 3i plus 4j into from here to here point Q is a comma 0, right? So it is ai plus 0j plus this part value of force is same again, if the force is acting same, 3i plus 4j, and this displacement you can write it in this way, this vector, it is 0i plus aj. I believe the idea is very, very clear. Here along this you are not moving along anything along x-axis, it is the entire displacement is happening along the y-axis for a unit. So aj is the displacement, right? So just multiply it. So this is going to be 4 into 0, 0. So it is 3a. This is 3a plus, and 3 into 0 is 0. 4 into a is 4a. Again 7a. So what we have understood from this part, this question is very important and it is explaining us a very interesting idea, that if you are moving a body from one point to another point, right? In that situation, provided there is no friction and there is no such forces, right? We will talk about that in conservative, non-conservative forces. But if the body is moving from one point to other point, you have seen it that the value of work done remains same along both the paths, right? So value of work done does not depend on the path, right? In these situations, under we call such forces as conservative forces, by the way, right? So yeah, so option number 1 is going to be the correct option. So a particle of mass 0.5 kilogram is displaced from the R1 to R2 by applying a force of magnitude 30 Newton, which is acting along I plus j plus k. The value of work done of the force. Okay, so this is the good question, slightly good question, calculation wise. So particle of mass 0.5 kilogram. So mass is given 0.5 kilogram. Okay, it is displaced from this point to that point. So the value of displacement vector will be this minus this. So 4i minus 2i is 2i only, right? 3j minus 3j is 0, and this is 1, this is 2, right? So it is 1k, sorry, right? So you can write down the position vector of the first point is 2i, 3j and 1k. Position vector of the second point is 4i, 3j, 2k, right? What will be the displacement vector? This vector minus that vector. So you see that the coefficient will be subtracted. 4 minus 2, which is 2, right? 3 minus 3, which is 0. 2 minus 1, which is 1, right? So this is the displacement vector. Now, this is the first thing you need to calculate, the displacement vector. Now, the second thing is by applying a force of magnitude 30 Newton, which is acting along this, right? So how will you write down the force in the vector format? Displacement vector is written, force vector is not written. So force vector you can write down the magnitude of force into unit vector in the direction of force. You know that any vector is magnitude of that vector into unit vector. You can just multiply them and get the full vector. So what will happen? Here the value of force is this. What will the value of force? A magnitude of force 30 Newton. So this part is 30 Newton. Now this force is acting along this vector. So how will you get the unit vector in this direction? So unit vector in any direction is just the vector upon its magnitude, right? Let's say that a vector is magnitude of this thing into unit vector. So what will be the unit vector in any direction? The complete vector upon the magnitude of this thing, right? So unit vector, the force is acting along this vector. So what will be the unit vector in this direction? You can say that the complete vector I plus j plus k upon the magnitude. So magnitude is under root coefficients square. So under root 1 square plus 1 square plus 1 square, which is under root 3. So I believe the idea is very, very clear. This vector and this vector are written. You just take the dot product of these two and you'll get the answer, right? So just take the dot product of these two and you'll get the answer. So here you have it. R1 and R2 are written, right? So just subtract them and you will have the displacement vector first of all, right? Okay. Now once you have the displacement vector, then you can go ahead and talk about the force vector as well. So force vector will be magnitude of force into the unit vector. This whole thing is the unit vector. You see that? The entire vector I plus j plus k upon the magnitude. So the same thing is written over here, right? The force vector is also there. So just take the dot product of these two and you will have the final answer, right? The dot product of these two and you'll have the final answer. And dot product is also very, very easy. Just multiply the coefficients. That's it, right? Now the work done by the force F is minus 6x cube I vector, I cap, is displacing a particle from 4 to minus 2. So what will be the value of work done? My dear kids, here the force is dependent on x, right? So it is changing with the displacement. So here it is a constant force or a variable force. Here we have the force is a variable force. And if this force is variable, my dear kids, you can talk about this idea. If the force is variable, then what will the value of work done? What will the value of work done by that force? Integration of f dx, right? So integration of, just integrate this part. So it is minus 6x cube. So it is going to be 6x to the power 4 by 4. Integration of x cube is x to the power n plus 1 upon n plus 1. So x to the power 4 plus 4. And you just put the limits. The limits are 4 to minus 2, right? So just limits are 4 to minus 2. So that's it. Just put the upper limit minus lower limit and solve it and you will have the answer. In place of x, put minus 2, then in place of x, put 4 and just solve it. So over here you have it. Just integrate it. You have integration of 6x, integration of this thing, right, is there, and just put the value over here. Okay. All right. Now let's move on and talk about the next idea. Okay. Let's move on and talk about the next idea. Over here we have it. So a block of mass 10 kilogram is moving along x-axis under the action of force 5x Newton. The work done by the force in moving the block from 2 meter to 4 meter will be. So you see that a block of mass is there. It is moving along x-axis and the force is 5x Newton, right? The work done by the force in moving the block from 2 to 4 meters. So integration karna padega. We have to integrate this thing. So what the value of work done will be integration of f dx, right? We have to integrate it from x equals to 2 to x equals to 4. So force is 5x. Integration of that is going to be 5x square by 2. Just integrate it from 2 to 4. Put the upper limit 4 square by 2 minus lower limit 2 square by 2. That's it. Just solve it and you'll have the answer, the value of work done. Right. So that's it. Now in this question, have a look at this question as well. A body of mass 50 kilogram is lifted to a height of 20 meters. So from here we are lifting the body, right? 20 meters from the ground in two different ways. Okay, so this is the surface, right? This is the surface. You can stand over here and lift the body like this directly, right? Or you can stand over here and push the body all the way to the point, right? End result is same. The body is moving from the base to this point, right? From the base to this point, right? End result is same, right? In this situation, what will be the difference of work or ratio of work done, right? So in the first part, when you're moving in this path, the work done is W1, and when you're moving from this path, the work done is W2, right? What will be the ratio of work done? My dear kids, over here you can say, because the displacement from this level to that level is same, or displacement in the vertical direction is same. So what will be the value of work done in these situations? The ratio of work done against the gravity we are talking about. So gravitational forces are acting downward, right? In this situation also gravitational forces are acting downwards, right? So here you see that the displacement in this direction is again same in both the cases. So work done will not depend on the path and the ratio will be 1:1, right? The ratio is going to be 1:1. The force is this, displaces the body from 2 to 4. Work done by this force is going to be. So work done by the force, because it's a variable force, you have to integrate it. 3x square plus 2x minus 5. Just integrate it and get the value of work done. You have to integrate it from 2 to 4. So integration of this is going to be 3x cube by 3. Integration of this is going to be 2x square by 2. And this is going to be 5x. Just put the limits 2 and 4 and just solve it. Put the upper limit minus lower limit. So you have it. 3 and 3 will cancel, 2 and 2 will cancel. So put the upper limit 4 cube plus 4 square minus 5 into 4 minus lower limit 2 cube plus 2 square minus 5 into 2. I hope the idea is very clear. Right, that's it. A force of that many newtons displaces the body from 2 meters to 4 meters. The work done by the force is. So again the same thing, right? It's the same numerical. So now have a look at this thing. The concept of kinetic energy. We have understood the value concept of work done and how to calculate the work done by constant force as well as the variable force. Now look at different types of energies and relate the work done with the energy, right? It's a very interesting relation. Let's have a look at that. Kinetic energy, you know that when a mass moves with a certain speed v, right, then it carries an energy within itself, right, or a moving mass carries an energy with itself, and that energy has a name called as kinetic energy, right. So what will happen? Kinetic energy of the body is going to be half mv square. If a mass m is moving with the speed v, the kinetic energy it's going to carry is half mv square. I believe the idea is very clear, right. Next thing is, now if the mass m is moving with the speed v, it will have one more quantity of physics related to that, and that is called as momentum, right. So how will you define momentum? Momentum is simply mass into speed, right. Mass into, it's a vector quantity, so mass into mass and vector velocity is multiplied in that way. But here we have it, we are just talking about the magnitude over here. So the magnitude of momentum of the body can be related to the magnitude of kinetic energy. So kinetic energy, by the way, is a scalar quantity. You can relate it in any way, right? So these two things can be related directly. How can you relate them, right? Momentum depends on mass and velocity. Kinetic energy also depends on mass and speed, or you can say that magnitude of momentum depends on mass and speed, right? And kinetic energy depends on mass and speed as well. So we can find this in this, right? We can relate kinetic energy and the magnitude of momentum of the body. How? Kinetic energy is half mv square, right? It's half mv square. So just multiply and divide by m. Multiply and divide by m in the numerator and denominator, right? So m square upon m. So m square v square is mv whole square, which is the square of momentum and twice of mass. So this is the relation between kinetic energy and momentum. Kinetic energy is the square of momentum upon twice of mass. So this is a very simple relation. Kinetic energy is square of momentum upon twice of mass. To go look at the question. A man has a box that weighs 10 kilograms. The current energy of the box when the man runs with a constant velocity of 2 meters per second along the box behind the bus is. So doesn't matter what is the weight. So it should not be the weight. It should be the mass. Weight is not the correct word. It should be the mass, right? Okay, so the kinetic energy of the body is half mv square. You have to find the kinetic energy. So half m is 10 kilograms and square of velocity 2. So just solve it, right? 20 joules. So option C is correct. Let's move on to the next one. 120 gram mass, 120 gram, that is 0.120 kilogram, is moving with this velocity 2y plus 5j in a certain at an instant. Find the kinetic energy. So kinetic energy, we don't need velocity in a vector format. Find the magnitude of velocity or the speed. It is under root this square plus this square. So 25 plus 4, it is under root 29. Kinetic energy will be half mv square 0.120 into this square. So under root will be removed and 29 will be there. Just multiply it and you will have the kinetic energy. A body is moving under the action of force. Suddenly the force is increased in to such an extent that the kinetic energy is increased by 100%. Kinetic energy, if it was k initially, right, k1, if you say that k, it is increased by 100%. So the final kinetic energy is 2k. Okay. So if you are increasing the kinetic energy, the momentum, the magnitude of the momentum will also increase. We have to talk about by how much percentage the magnitude of momentum increases. You know that the kinetic energy is the square of momentum upon twice of mass, right? So this is k1, p1, m1. k2 is going to be p2 square upon 2m2. My dear kids, here we are moving the same body in both the cases. When the kinetic energy was k and when the kinetic energy was 2k, the mass was same, right? Since the mass was same, so m1 and m2 are same and they can be cancelled. 2 and 2 is going to be same, that can be cancelled as well. So ratio of kinetic energy is square of ratio of their momentums, no problem. Kinetic energy, this is k, and instead of this thing you can place 2k. So k and k can be cancelled. So P1 square upon P2 square is 1 upon 2, or you can say that P1 upon P2 is 1 upon root 2, or you can say P2 is going to be root 2 times P1. No problem with that. So with how much, what is the percentage increase in the momentum right now? So percentage increase in the momentum is delta P upon P into 100. So you see that final momentum is root 2p, initial is p upon p into 100. You see that p is cancelled, so it is root 2 minus 1, right, into 100. So it is 1.414 minus 1, so 0.414 into 100 approximately. So it is 41.4%, right? So roughly it is option C, you can say that, right? So roughly it is option C, yeah. Let's look at next question. Two solids A and B of mass 1 and 2 are respectively. They are moving with equal linear momentum, okay? So they are moving with equal linear momentum. The ratio of their kinetic energies will be A is to 1. So what will be the ratio of A? Very simple. So kinetic energy is square of momentum upon twice of mass. And now you see that two solids A and B of mass 1 kilogram and 2 kilograms. So masses are not same. K2 is going to be P2 square upon 2m2. It is given in the question that they have equal linear momentum. So P1 and P2 are same, right? So P1 square and P2 square will be cancelled. So you see that the ratio of kinetic energy is coming out to be opposite of ratio of masses, right? If the momentums are same, and masses are 1 kilogram and 2 kilogram. So m2 is 2, m1 is 1. So ratio of kinetic energy will be 2 is to 1. So 2 is to 1, 2 is to 1, that means A is 2, right? So ratio is 2, right? Two bodies are having the kinetic energy in the ratio of 16 is to 9. So ratio of kinetic energy in two bodies is 16 is to 9. If they have the same linear momentum, the ratio of their masses will be. So clearly you say that kinetic energy is a square of momentum upon twice of mass, a square of momentum upon twice of mass. Let's say m1 and this is this, right? So as they are writing that they have the same linear momentum, so P1 and P2 are same, right? 2 and 2 is same. You see that in the previous numerical as well you have seen, if the momentum is same, the kinetic energy has a ratio of opposite of masses. So clearly you can say that kinetic energy is 16 to 9. The ratio of masses is m2 upon m1 is 16 to 9. So m1 upon m2 will be 9 upon 16, right? The ratio of their masses is 9 upon 16. So option B is going to be correct option. No problem with that. Now we have seen that what is work, how to calculate the value of work done by constant force. We have also seen how to calculate the value of work done by variable force. We have also seen how to calculate the kinetic energy in different situations, right? And how to deal with the kinetic energy and momentum together, right? Now our duty is to deal with this thing, work energy theorem, right? Let's understand work energy theorem, how to talk about that. Here, if a body is acted upon by multiple forces, right, it is possible that the body is moving and lots of forces are there to move the body, right? As you remember, right, Jagannath Puri, there's a huge chariot and lot of people are pulling that. So lot of forces are acting on the body, right? So you see that work done by all the forces acting on the body reflects in one form, and that is by changing its kinetic energy, right? If lot of people are doing work, right, but the body doesn't move. If let's say huge chariot is there and only 50 people are pulling it, so because the chariot is so huge and heavy, 50 people won't be able to pull it, but they are applying some force. Displacement is 0. So what will the value of work done? 0. And since the value of work done is 0, you will find that the chariot doesn't move at all, right? The chariot has 0 kinetic energy, or change in kinetic energy of the chariot is 0, right? That means if you don't do any work, kinetic energy is not changing, right? So you see that work done by all forces reflects by changing the kinetic energy of the body, right? That's it. This is the simple form of work energy theorem. Okay. A particle of mass 0.1 kilogram is subjected to a force which varies with distance as shown in the figure. It starts, if it starts the journey with at rest from x equals 0, so it is starting with the initial velocity 0, right? Then what is happening? The force is acting on the body like this. It increases, becomes constant, and then it decreases, right? So the force is changing on the body, okay? And what is happening when the body eventually is there, when the force becomes 0 at the end, right? What is the new velocity the body might have achieved? Think about it. The force is acting on the body. The force is acting on the body, right? So the body is we are working on the body, right? And since we are working on the body and the body is displacing as well, so we see, you have just understood that whatever work you have done will reflect in the change in the kinetic energy, right? We have done some work, the body has started to move, body has gained some kinetic energy, right? And since the value of force is changing and all that is happening, the velocity and all that will change as well, and the body will have some kinetic energy at the end, right? Okay. So how much kinetic energy it has acquired? By work energy theorem, we can say that the increase in kinetic energy of the body is equal to the amount of work done. Initially the body was at rest, so initial kinetic energy was 0. Let's say the final velocity at the end when the force stops is v. So final kinetic energy is going to be half mv square. Initial kinetic energy will be 0, right? And how much work you have done? In this situation, you can say that force is not constant. If force was constant, the value of work done would be fd cos theta. Here the force increases, becomes constant, then it decreases. So in the entire journey, the force was not constant. So you have two ways. Either you take the area under the curve, or in the calculus, the same way is the same method of taking the area under the curve is integrate if the expression is given. So here taking the area under the curve is easier, right? We have a trapezium. So the area under the curve will be 1 upon 2 into summation of this side and this side. So this side is 12, this side is 4 and 8, 4. So 12 plus 4, right? This is 12, this is 4 into distance between them. Distance between them is 0 to 10, only 10, right? So that's it. You just solve it and you have only one variable, that is velocity. Mass is already given 0.1. You can just solve it and get the final value of velocity, right? That's it. 40. A spring of a spring constant 1000 Newton per meter is compressed through 5 centimeter. So spring constant is 1000. It is compressed through 5 centimeter and it is used to push a metal ball of mass 0.1 kilogram. It is compressed. So how much compression you are getting? 5 centimeter. And it is used to push a metal ball of mass 0.1 kilogram. Okay. So first of all, you see, when I am compressing the spring by a certain value, so I have done some work, and that work is not wasted. That work is stored as a form of energy in the spring, right? Now, in the compressed situation, if I place a ball in front of it and I release it, right? So what will happen? The ball will shoot away in the forward direction. My dear kids, the energy the ball is going to get is because of the stored energy in the spring, right? If I am storing 10 joules energy in the spring, it can only transfer, if it transfers all of it, 10 joules to the ball in front of it. Yes or no? So here we have it. By compressing the spring, how much energy we have stored, we can say the amount of work we have done gets stored in the spring. So basically, the value of work done is half kx square, right? And that is the value of energy stored in the spring during compression. So we can say that energy stored in the spring is energy stored in the spring becomes what? Kinetic energy is provided to the kinetic energy of the ball, right? It becomes the kinetic energy of the ball. Okay. So energy stored in the spring is half kx square, and kinetic energy of the ball. What is the kinetic energy of the ball? We can say that, or you can say energy stored in the spring will change the kinetic energy of the ball. So this is the change in the kinetic energy of the ball. Initial kinetic energy was 0. final will be half mv square. Now, everything is given. The value of k is given 1000. The value of x is given 5 × 10⁻². The value of mass is also given. The mass of the ball is 0.1 kilogram. Mass is also given. You can calculate the value of velocity from here. So this is the key expression. And by solving it, you can calculate the value of velocity. So just solve it. Half and half is cancelled out. The value of k is 1000. Right. The value of x is 5 × 10⁻² squared. The value of mass is 0.1 kilogram. And the value of velocity square is there. So V you can calculate from here. I believe the idea is very, very clear. Okay. Now the next thing is there. As shown in the figure, a particle of mass 10 kilogram is placed at the point A. Particle is placed over here. When we are slightly displacing to the right, so particle will start falling downward, right? So right now it has potential energy. It is now converting into kinetic energy. It is getting faster and faster, right? It has stored some energy in it when it is at a certain height, and all that energy is converted to the kinetic energy when it is falling down. It is getting faster. So the speed of the particle when it is reaching the point B, right, we have to calculate, right? So the value of x to the nearest integer is, okay, no problem with that. So here, when the particle is over here, it has some potential energy, and that potential energy is converted at this point to the kinetic energy, right? So we can say that over here, what is the potential energy in the body? So see that, let's take this as a reference. Okay. So let's say that over here, the potential energy is 0. So from this point, the total distance is 10. This is 5. So here you have 5 only. Okay. So the potential energy reference to this one is mg5. Okay. This is the reference level. This is our new reference. So potential energy with respect to this reference is mg into 5, m into g into h, right? And the kinetic energy over here is half mv square, right? So mass is cancelled out. The value of g, let's say, is 10, and the height is it has travelled is only 5. Okay. So half v square is v square. So it is 50 into 2 is 100. Velocity is going to be 10 meter per second when it reaches at point B. Right. Let's move on and talk about the next idea. The ball of mass 4 kilogram is moving with a velocity of 10 meter per second. It collides with a spring of length 8 meters. So a ball of mass 4 kilograms is moving with a velocity of 10 meter per second. It has what? Kinetic energy. What is that kinetic energy? Half mv square. It is moving ahead. There was a spring. Okay. This is the spring. Okay. So it is colliding with a spring of length 8 meters and force constant 100 Newton per meter. The length of the spring is compressed by x in meters. So initially the total length of the spring was 8 meter, right? And when the ball that carries some kinetic energy, right, it will simply go ahead and strike the spring will get compressed. The spring gets compressed, let's say till here, by a value x. So the remaining length would be 8 minus x. Okay. All right. So the spring is compressed. The length of the compressed spring is x. Sorry, the length of the compressed spring is x. It is not compressed by this amount. You see that the question is saying, read the question very carefully. The question is saying that the length of the compressed spring is x. Okay. So when the ball is going to hit, the spring will not remain 8 meters. It will become lesser. It will become compressed. And let's say that when the spring is compressed, it looks like this. Okay. So while it is compressed, the new length is x. Okay. It is not saying that it is compressed by the x units. It is saying that the length of the compressed spring whole is x, right? Okay. So by how much amount it has been compressed? This value is 8 minus x. Okay. All right. The value of x to the nearest integer is, okay, we can calculate that. This is, let us say, is change in this is the deformation basically, right? My dear kids, when we are deforming this spring by delta x, how much energy are we end up storing? We can say that half k into deformation delta x square, right? Okay. So we can say that whatever kinetic energy the ball had, right, it will be invested in the form of spring's potential energy, which is half delta kx square, right? So half mv square is half k delta x square, okay? Half and half can be removed. Mass is given 4 kilogram, velocity given 10 meter per second. K, the value of spring constant is 100, and the deformation we don't know, right? So 100 and 100 will cancel out. Delta x square is 4, so delta x deformation will be 2 meters, okay? So we can say that when the ball is hitting the spring, it gets deformed. Delta x is 2 meters. Delta x is 2 meters. So this part is 2 meters. The total length was 8 meters. So the value of x is 8 minus 2, 6 meters. Okay. The value of x is going to be 6 meters. So the value of x is going to be 6 meters. I believe the idea is very, very clear. Let me explain it one more time very quickly. Right. Just takes 30 seconds. Right. So here what is happening? The ball is moving. It is striking the spring. The ball is transferring its kinetic energy into the potential energy of the spring, right? The spring is deforming by the value delta x, so the spring is going to have the potential energy half delta kx square. The ball is moving with velocity v, so it has kinetic energy half mv square, right? This energy is being transferred into this form, they must be equal, right? When we equal them, we get the deformation value, and we need to know that during the compression what is the new value or the value of x. So we can say that the value of x is going to be the total value minus deformation, which is 6. So 6 is the answer. All right. Now, in this question, the question is saying that a particle experiences a variable force 4x I cap 3y square j cap in a horizontal xy plane. Assume the distance in meters and force in Newton. If the particle is moving from point 12 to point 23 in the xy plane, then the kinetic energy changes by. My dear kids, the kinetic energy changes by the value of work done. By work energy theorem, the value of work, by the change in kinetic energy is basically equals to the value of work done. Here, force is variable, 4x I cap 3y square j cap. Because the force is variable, the work done will be calculated by simply integration, right? So work done will be integration of f dx, right? Or we can say that integration of fx dx plus integration of f, because the force is a function of x and y and z as soon as, right? So when you want to talk about the value of work done by such a force, you can integrate by all other variables. So fx dx plus fy dy and so on, fy dy. All right. So integration of fx dx, integrate that 4x. So you have 4x square by 2. Okay. Integration of 4x is 4x square by 2 plus integration of 3y square is 3y cube by 3, right? And you see that the value of x is changing from 1 to 2. You see that particle is moving from the value of x coordinate is changing from 1 to 2. So x coordinate is changing from 1 to 2, and the y coordinate is changing from 2 to 3. Y coordinate is changing from 2 to 3. So just integrate, just to put the values now and solve it, you will have your final answer, right? Just put the values and you will have your final answer. Now, let us talk about two different types of forces, conservative and non-conservative forces. In one of the numericals that we have solved, my dear kids, we have seen that the work was done in two different paths, right? The particle was moved from this point to that point in this path and along this path, right? We found that the value of work done came out to be same. Along this path, if work done was W1, and around the other path, if the work done was W2, we found that W1 and W2 was same. My dear kids, this is true for all situations when the force is of certain type. That's something I told you back then as well. What is the type of force? My dear kids, the work done by a force is going to be independent of part taken only when the force is conservative by nature. But my dear kids, you can ask, what is a conservative force, sir? So here we can say that a force is called conservative when the work done by the force depends only on the initial and the final position and not on the path traced, right? So the work done is conservative when the work done by the force is independent of path. of path. All right. And my dear kids, this kind of conservative force or this kind of work done by the conservative force gets stored in the body in some form, right? Gets stored in the body in some form. So here you have it. If you take the body from point A to point B, right, along this path, so we can say that you have worked against gravity, right? So work done by the gravity is stored in this body, right? And if you take it along this path as well from the point A to point B, initial and final point are same, right? So if you follow the path number 1 or you follow the path number 2, work done will be same because gravity is the conservative force, right? So in this situation, in both the paths, we can say that the work done will come out to be same, right? So gravity will be a conservative force, okay? Now, one more thing about the conservative force, if you start and come back to the same place, the total displacement is going to be 0, right? So the work done by the conservative force is also going to be 0, right? So you started at A and came back at same point. So in this loop, the work done is going to be 0, right? Examples of conservative force: electrostatic force, gravitational force, spring force, etc., right? And this is a very, very interesting point, and this note is very, very important. You see that the concept of potential energy always and only applies to the conservative forces, right? Potential energy is a form of stored energy. Think about it. Friction, right? Here you have a surface and you, let's say that, move a body from point A to point B on the surface. In the entire journey, let's say the friction was acting backward, right? Friction is acting this way, displacement is this way, right? Friction has done some work, Fd cos 180, right? That will come out to be a non-zero value, okay? With a negative sign, it will come out some value, let's say minus 10 joule. My dear kids, whatever value you got, minus 10 joule, it is totally unrecoverable, right? And that minus 10 joule cannot be stored in the body in any other format because that will be wasted in form of heat into the atmosphere, right? So work done by friction cannot be stored. So the concept of potential energy, the stored energy, cannot be linked with the friction itself, right? You see that here the spring forces can lead to some energy being stored in this spring system, right? In this system, the spring forces are there and the energy is being stored, half kx square, right? But the work done by friction, right? When the friction is involved, that work done by friction is not getting stored anywhere. So friction is not conservative by default. So there is no concept of potential energy associated with friction, right? Friction is a non-conservative force, You see that you move a body along this path on the table or you move a body along this path on the table, the work done by the friction will be entirely different. You can also do that with the help of a chalk, right? The chalk will, if you rub the chalk on the blackboard, what will happen? The length of the chalk will reduce, okay? More you rub, more work will be done by the friction and more reduction in the length you will get, right? Now, if you move along a smaller path, you will get lesser reduction because friction has done lesser work. And if you move the chalk along the board, along the table or the board, along a bigger path, the length will reduce by a greater distance, and hence we can say that the friction has done more work. So clearly you can say that work done by friction depends on the path, right? Work done by friction depends on the path, and all the situations are there, right? If you take the chalk and make a 0 out of it, so what will happen? Chalk will still reduce its length, right? So clearly we can say that work done, chalk will still reduce its length when it is, so what will happen? We can say in the closed path, work done by friction was not 0, right? So if you have a non-conservative force like friction, so we can say that a force will be non-conservative when the work done by the force moving a body depends upon the path between the initial and final positions. Work done is in a closed path is not 0 in a non-conservative force field. Clear? So frictional force and all velocity dependent forces such as air resistance, viscous forces, they are all non-conservative forces. So that's the basic difference between them. In a table format, you can have a look at that as well. So conservative force, work does not depend on the part taken. Here the work depends on the part taken. Work done in round trip is 0, in a loop is 0, and work done by the non-conservative force in a loop is not 0, right? when only a conservative force acts within a system, the kinetic energy and potential energy can change. However, the mechanical energy of the system does not change. Very important, right? When the system has conservative forces only, so what will happen? Imagine that we have a ball, right? Imagine that this is the system, this is the ball, right? Right now it has potential energy, kinetic energy is 0, so mechanical energy is kinetic plus potential energy is mgh, kinetic energy is 0, right? So all the mechanical energy is only in the form of potential, right? If I drop it, so what is happening? During every point, its velocity is rising, and since the distance from this base is, the reference is reducing, its potential energy is reducing, right? When it touches the reference surface, what will happen? Potential energy is basically 0 for this reference, okay? So what will happen? The potential energy is reducing, but whatever reduction is we are getting in the potential energy, we get the same amount of increment in the kinetic energy. You see that? The body initially had 100 joules of potential energy, let us say, and 0 joule of kinetic energy. This is the total mechanical energy of 100 joule, okay? So it is dropping, and at the bottom, just before hitting the ground, all the potential energy has been converted to the kinetic energy, right? Okay, and at any point in between, potential energy and kinetic energy both are there. Maybe potential energy here it is, let's say 60, and kinetic energy is 40. At any other point, let's say potential energy is 20, kinetic energy is 80. But the total summation is constant, because in this journey, only gravitational forces are acting, and gravitational forces are conservative forces, right? So if the conservative forces are acting in the picture, then the mechanical energy of the system will remain same, it will not change, right? Here, work done against non-conservative force may be dissipated as heat energy. Yeah, we know that. Work done is completely recoverable. Yeah, in this situation, work done is completely recoverable, right? Whatever we can say over here. We can also have a look at over here. So here you can see you have done some work, right? But whatever work you have done is not wasted. It is stored, because the conservative forces, the spring forces are involved, and it is recoverable. How? The spring will bounce back, right? So it will simply perform some work if you place a body right next to it. So what will happen? Work done by conservative forces are recoverable. If you take a body, lift it from here to here, so we can say that work done by the gravity is not wasted, right? It is stored in the body and it can be recovered. If you release it, all that work you can get back, right? Work done by friction is not recoverable, right? If you are moving the body against the surface, so you see that whatever work is done against friction, that is simply wasted, you cannot get it back. The next thing is about the energy, right? Energy, what is energy? Energy is simply the ability of the body to do work, right? Energy is ability of the body to do work, right? SI unit is going to be joules, CJS unit is ergs, 1 joule is 10 to the power 7 ergs, right? So these things you know. There are different forms of energy, right? The main form of mechanical energy we talk about, because mechanics we are dealing with. Mechanical energy has two forms, kinetic and potential. Kinetic energy is due to the motion of the body, and potential energy is due to the position of the body, right? So the word potential energy is very, very important. Kinetic energy we have understood. Let's talk about the potential energy in detail, okay? Potential energy. The potential energy is there in the body because some work was done and that work got stored, right? Or you can say that the body is in a very specific configuration, and because of that configuration, the energy is stored in the body, okay? How do you understand that, sir? If you take the bow and arrow, right? Initially, there is no potential energy stored in the string of the bow and arrow, but, or you can say in the system of bow and arrow, no potential energy is stored. But when you stretch the string of that bow and arrow, what happens? In the system of this thing, some energy is stored, right? And when you release it, that energy, that stored potential energy can shoot the arrow forward. I believe that is very clear, right? You see that potential energy can be thought of as stored energy that can either be work or can be converted to the kinetic energy, right? So yeah, so in this toy thing, right? So you can just wound the spring and that will do the work. So there are different types of potential energy: gravitational potential energy, elastic potential energy, right, and others. So this is very important. Potential energy is only described in the conservative force field. Conservative force field is like gravitational field, electric field, magnetic field. Potential energy is only defined in these conservative force fields, right? Non-conservative forces like friction force, viscous force, in these situations, the potential energy is not there, right? Potential energy is always defined relative to some absolute value of potential energy, cannot be calculated. So here, we are saying that the potential energy is always defined relatively. Here, let's say that we have one table. On the top of a table, we have a smaller table. On the top of a table, we have even a smaller table, right? Like this, right? So you see that if I keep a body over here on the top of the topmost table, so what will happen? This is point A, this is point B. Let's say that this is 5 meters. The topmost table is of 5 meter tall. It's a very tall table, right? So what is happening? The potential energy can be described with respect to this reference mgh, right? But think about it. We can also describe the potential energy from here to here as well. And let's say that this is 10 and this is 15, right? So if you want to describe the potential of the body for this reference, we have to take this height. If we are describing the potential energy of the body for this reference, we have to take this height. If we are describing the potential energy of this body for this reference, we have to take this height, okay? So you can define the potential energy after defining the reference, right? That's what I had done when I was explaining you a question, when a body was moving from this point to that point, right? You remember, right? First of all, what I did was I defined the reference. I said that let's take this as a reference, this point as a reference, and then I took this distance was 5, right? Otherwise, if I had to take the total distance from the ground, I would have taken 10, right? And then mgh equals to change in kinetic energy. I have done that, right? So whatever, right? So over here we have it. Potential energy is going to be this thing, right? Work done will reflect in a change of potential energy. Work done by the conservative forces. WC is work done by the conservative forces will reflect in the form of change in potential energy as well. So here it is, right? So force is, so integration of this thing is giving you that, right? Fx dx is giving you the change in potential energy. So you simply you can just make the things like that. So force, a small change in potential energy is F dx, right? You can say that this is the value of work done. If you are displacing the body by dx by a force F, the value of work done will be F dx. This is how much work you have done. And if the work is done by the conservative force, if that force is conservative, then work done by the conservative force WC is F dx. That will be change in potential energy du. Is that clear? Right. So how can you get the value of force back? It is du over dx. Okay. Minus sign is there as well. So what do you mean by the minus sign? Minus sign is showing you that. What do you mean by the minus sign over here? So minus sign can have different meanings, but the most profound meaning of the minus sign is that the systems are bound generally, right? And if the system has negative potential energy, that means the systems are bound. For example, if two particles have a combined potential energy as negative, that means you have to supply some energy to separate them, right? Over here, what is the meaning of negative sign? So we can clearly say that. Right now, whatever work is done, initial potential energy was lesser and final potential energy is higher. So just to keep the whole thing positive, we are introducing that minus sign, nothing big, right? Just because you see that initial will be lower. Whatever work you have done, that has increased the final value. So this is the bigger value, this is a smaller value. So a smaller value minus bigger value, the change will come out to be negative. So that's why we have negative sign, right? So no need to worry about that. So force is minus du over dx, right? Okay. All right. So yeah, this is by differentiating potential energy, you can get the value of force acting in that situation. Nothing very serious about that. Right. For the spring, the potential energy is going to be half kx square. When you compress the spring, what is the value of work done? Because the force is kx. Force is kx. Integrate that. Right. Force is minus kx. Integrate that. So half kx square will be the value of work done, and that will reflect as a stored energy. Half kx square is the stored energy. Right. Okay. Now, we can also have the non-conservative forces acting in the picture. My dear kids, if non-conservative forces are acting into the picture, in that case, the mechanical energy of the system will not remain same, right? Mechanical energy of the system will not remain same. Work done is work done by conservative and non-conservative forces both. Then, in that situation, what will happen? The total work done is change in kinetic energy, right? We have seen it by work energy theorem. So work done by conservative force is only the change in kinetic energy, change in potential energy, sorry, right? Work done by conservative forces will reflect as a form of change in potential energy, right? Whatever conservative forces have done, whatever conservative forces are there, whatever work they have done, that will be stored in the body in the form of potential energy, right? So we can say that delta U plus WNC, you see that work done by conservative force is this. Work done by conservative force is equals to change in the potential energy. Just put it over here. So work done by non-conservative force is going to be, you can take that part over here, right? So delta K plus delta U. So what will that give us? It will give us like this, right? UF minus UI plus KF minus KI, right? So what does that tell us, right? UF plus KF is final mechanical energy. UI plus Ki is initial mechanical energy. So in short, work done by the non-conservative forces is equals to change of mechanical energy of the body. Okay, understand one more time, or let's try to have visualize it. So it's a very weird expression, and it seems as if it is complicated, but it is not, right? Here it is, the body is at A, right? If there was no friction, if there was no air friction, let us say, right? So body had initial total energy 100. Right now all the energy is in form of potential energy, right? 100 joules of potential energy is there, and 0 kinetic energy is there, right? The body starts falling. We said that if there is no friction, nothing. So what will happen? Let's say potential energy is now 80. So the remaining 20 is the kinetic energy. But my dear kids, if the friction is acting, what will happen? Some of the energy, some of the work will be done against friction, and the body will get heat up like a meteor when it falls, right? It heats up and wastes some energy in the form of heating, right? So it slows down. So what will happen? Because of that friction, some energy will be wasted in form of heat, and it will slow down, right? So it will not gain as much kinetic energy as it should have. So the potential energy is from 100 to 80, but the remaining energy, a part of the remaining energy is wasted already. So now you have only 18 joule, let's say, kinetic energy left. 2 joule was wasted in form of heat, right? So you see that the remaining total energy is only 98. Okay, you started with 100, now it is 98. 2 joule was wasted against friction, right? So what was the work done by friction? We can say that 100 minus 98, which is 2 joule. 2 joule work was done against friction. So initial mechanical energy was 100. Over here the mechanical energy is 98. So those 2 joules that were wasted, that is wasted by the non-conservative force, or the work done by the non-conservative force over here is change of mechanical energy. Simple, right? So work done by non-conservative force is change of mechanical energy, right? Okay, so if there is no non-conservative force, the mechanical energy will not change. Clearly, yeah, we can say that. So energy conservation. Yeah, energy conservation. So very simple idea. Mechanical energy is only conserved when the non-conservative forces are not acting into the picture, right? Here you have seen it. If the friction or see these things are acting, then the mechanical energy will not remain conserved, right? Some of the mechanical energy will get lost, right? Mechanical energy will not be conserved if the non-conservative forces are acting into the picture, right? So under which condition the mechanical energy will be conserved? Only when the non-conservative forces are 0, right? But the total energy of the system remains conserved in all cases, right? The total energy is mechanical energy plus thermal energy plus all other forms of energy, right? So we can say that the total energy is conserved in all other cases, be the forces acting on the system are conservative or they are non-conservative. Clear? So that difference should be very clear in your mind, right? Now look at this question. The potential and kinetic energy of a helicopter flying horizontally at a height of 400 meter are ratio of 5:2. The velocity of the helicopter is, what will be the velocity of helicopter, right? So here it is. The potential and kinetic energy of the helicopter is, the ratio is given 5:2. at a height of 400 meters. So no problem. Potential energy is mgh and kinetic energy of the helicopter is half mv square. So mass is cancelled out because the same helicopter is there. The value of g we can take as 10. H is 400, right? H is 400 meter. V is the only variable, you can just solve it. So you have 4000 upon V square is 5:2. You can simply solve it. No worries about that. A particle is moving in a conservative force field. Conservative force field, we will talk about the potential energy from point A to point B. UA and UB are the potential energy of the particle at A and B. WC is the work done by the conservative forces in this process. So WC, so what will be the value of WC? Okay, so particle is moving from A to B in the conservative force field. So what will be the value of work done by that conservative force? So work done by conservative force is negative of change in potential energy. Negative of change in potential energy. So you see that negative of UB minus UA. So it is clearly UA minus UB. That's it. I believe the idea is very, very clear. Let's move on and talk about the next idea. Yeah. Now look at this question. The question is saying that a spring of a spring constant 8 Newton per centimeter has an extension of 5 centimeter. The minimum work done in joule in increasing the extension from 5 centimeter to 15 centimeter is. So what is happening, my dear kids? Here, when the spring had an initial extension of 5, right now some energy is already stored in the spring, okay, and you have already done some work for that. And now what you want is, you want to extend it further from 5 centimeters to 15. Now you have done some more work and now a different amount of energy is stored in the spring, right? So you don't have to answer what is the total work done to extend for the entire 15. You don't have to answer what is the work done for initial 5 centimeter. You have to answer how much work was done in the extension 5 to 15, in between 5 to 15, right, in that difference, right? So clearly you can say that when the extension is 15, the energy stored is half k into 15 square. When the extension is only 5, the the work done the energy stored is half k into 5 square, right? So basically the difference of energies is the amount of work you need to deform from here to here. I believe the idea is very, very clear, right? You see what is happening over here. This is the spring. Right now the spring is not extended, it has no energy stored in it. When you extend it by little amount, you have already stored some energy in the spring, right? So half k x1 square, right? Now when you extend it further, now the new energy stored is half k x2 square, right, in the spring, okay? And that difference of energy is the energy you need to extend it from here to here, right? This is the difference it is being asked in the question, right? In the question what they are asking, the minimum work done in joule to increase the extension from 5 to 15, right? This difference is basically the amount of work you need to extend it from here to here. So the amount of work done to extend it from 5 to 15 is that difference, half k x2 square minus x1 square. I believe the idea is very, very clear. So half k, the value of k is 8, x2 square. So the deformation is in centimeter, so you can convert that in meters at any time. So x2 square is 15 square by 100 square. So 100 square I should have taken as common. I'll do that in the next step. x1 square is 5 square upon 100 square. I believe the idea is very, very clear. 100 square can be taken as common and you can solve the rest of it. So yeah. Now let's look at this question. On changing the length of a spring by 0.1 meters, there is a change of 5 joule in its potential energy. By changing the spring length by 0.1 meters or 10 centimeter, there is a change of 5 joule in the potential energy. The force constant of the spring is, very easy. So the value of the deformation, the value of deformation is 0.1 meter, and to deform that much you have to do some work, and the value of work done you need is half kx square. That is equal to the change of potential energy of the spring, right? So we can say that the value of work done or the change of potential energy both are same of the spring. That is given in the question is 5 joule. So that is 5. The value of k we have to figure out. The force constant of the spring we have to figure out. And delta x to 0.1 square. That's it. So from here you can calculate the value of k very easily, right? From here you can calculate the value of k very easily, right? Which is coming out to be 1000. A sphere of mass 2 kg is moving on a frictionless horizontal table. Okay, a sphere of mass 2 kg. A sphere of mass 2 kg is moving on a frictionless horizontal table with the velocity v. Okay, it strikes with a spring that has a spring constant of 1 Newton per meter, right? So it strikes with a spring of 1 Newton per meter. A sphere of mass 2 kg is moving on a frictionless horizontal table with the velocity v. Okay, it strikes with a spring. Okay, and it compresses it by 4 meters. So it is compressing it by 4 meters. So initially it had kinetic energy, and that kinetic energy is being transferred to compress it, right? So half mv square kinetic energy of the sphere is being transferred in form of the potential energy of the spring, half k delta x square. So half can be cancelled out. Mass of the sphere is 2 and the velocity of the sphere we don't know. A spring constant of that thing is given. Force constant or spring constant is 1. So value of k is 1. And the deformation you are getting is of 4 meters. Deformation, it is compressing by 4 meters. So just solve it. It is 16. 16 by 2 is 8. And under root 8 will be the answer. So 2 root 2 will be the answer. So option B is the answer. The force energy, the potential energy of a particle varies like this with distance as shown in the graph. The force acting on the particle is 0 at which point? So you know that the force, we have the potential energy versus distance graph, and from that the slope of this curve du by dx, right? That gives you the force acting on the body, right? Force is minus du by dx. You just differentiate the potential energy, and that's how you get the value of force acting on the body. Force will be 0 when the slope is 0. Force will be 0 when the slope of potential energy and the potential energy versus displacement curve is 0. So over here the slope is 0, over here the slope is 0, right? At all other points we have some slope, right? So but at point B and C we have no slope. So at these 2 points the force will be 0, right? Now, after talking about the concept of work, concept of energy, concept of work energy theorem, we can talk about the power. Power is, what is power? In day-to-day life, we talk about power is somebody is more powerful means somebody can lift more weight. But in physics, as the concept of work does not apply the same way, the concept of power does not apply the same way as we do in a common sense in a day-to-day life, right? The word power in physics means how quickly something can be done, right? The rate of work done is power, right? Power is how quickly something can be done. W by T. Average power is dW by dt, F ds upon dt, right? Average power is work done upon delta time, and instantaneous power, sorry, is dW by dt. Instantaneous power is dW by dt. Average power when an interval is higher is delta W by delta T, and instantaneous power is dW by dt, right? Yeah. So another way of writing the instantaneous power, this is also very useful format, right? It's a very useful format of writing power, instantaneous power. You see that work done can be written as F ds, and ds by dt is instantaneous velocity, right? So if you know the instantaneous velocity of a particle, right? So F dot v, this ds by dt is velocity. So F dot v can give you the instantaneous power of that particular particle, right? Okay, so this is the dimensions and all, right? Okay, now these 2 points are important. Have a look at these 2 points. So if you have work versus time graph, right? If you have work versus time graph, dw by dt will give you the instantaneous power, that is the slope of work time curve, right? So clearly we can say that the slope of work time curve dw by dt gives us the instantaneous power, right? The slope of work time curve gives us the instantaneous power, okay, dw by dt. And over here what we have, area under the work time area under the power time curve, So area under the power time curve will do the opposite thing, because power is dw by dt. So if you just take the area under the power time curve, so just take the dt on this side, so dw is p dt and integrate it. So area under the power time curve is represented by this calculus part, right? And if you are increasing from T1 to T2, so area under the power time curve is expressed by this thing, and it is representing the value of work done. So now we have it. By differentiating the work, or you can say that whatever expression of work is given, differentiating the work, you can get power, and clearly by integrating power you can get the work back. So that's the reason. And the physical significance, in the graphical significance, the slope of WT curve is power, and area under the power time curve is the work done. And these things are used in the previous years as well, which is why I'm explaining it multiple times, right? Power in this situation, when mgh work is done in a time t, so mgh work is done in time t, the power will be mgh upon t, nothing very serious. Power applied to a particle varies with time as this. So power applied to a particle varies with time with this expression, 3t square minus t plus 1, where t is in second. Find the change in its kinetic energy between t equals to 2 to t equals to 4. Okay, my dear kids, we have to talk about the change in the kinetic energy. Here we have a variable expression of power. It's a very good numerical, right? We have to find the change in kinetic energy. Change in kinetic energy will be basically the value of work done. Let's say you have done 100 joule of work, so that will be the change in kinetic energy of the body. Okay, now we know the power. Somehow if we can calculate how much work is involved in this situation, that work done will reflect as a change of kinetic energy. In the previous page, I have just told you this thing multiple times in the part 4 and 5, that if power is given, you can integrate the power and you can get the value of work done, right? Power you can integrate and get the value of work done. Very easily you can integrate it. Integrate the power with respect to time and you can get the value of work done. Okay. So just integrate it. It is 3t cube by 3 minus t square by 2 plus t. Okay. And here just put the value of time, which is 2 and 4. Alright. Put the value of time, which is 2 and 4. Put the upper limit and lower limit. You can get the value of work done from here, and the whatever work you get from this particular part, that will be reflecting as a change of kinetic energy, right? That's it. You see that integrated, put the upper limit and lower limit, and 46 joule is the value. That 46 joule is a change of kinetic energy. That is nothing but the amount of work done. Look at this question. A mass of body 2 kg begins to move under the action of time dependent force given by this thing. So force is variable force, okay? And the mass of the body on which this variable force is acting is 2 kg. The power developed by the force, okay, this is also a very good question, okay? So force is written as 6t I cap plus 6t square j cap. The power developed by the force at that time is going to be, so here, if you divide the force by mass, you can get the acceleration. Try and understand it. How can we talk about power when we only know force and we don't know the displacement, right? Think about it. Displacement is not given, right? The time is not given. Time is not given. So you cannot calculate work because force is given, displacement is not given, right? Or displacement vector is not given. So you cannot calculate the value of work done, and the time is also not given. So work upon time is power. So that you cannot calculate in that way, all right? But there is one more way to calculate the power, that is instantaneous power is force vector dot velocity vector, right? Force vector is given and velocity vector we can get, because from force vector we can get acceleration vector by dividing from mass, and from acceleration we can get velocity by by integration and differentiation. These things are related, right? Differentiating the velocity we can get acceleration, so integrating acceleration will get the velocity, right? Have a look at that. How are we doing it? Very simple, right? So clearly, we are very clear about the idea that power is worked upon time. That part we cannot do because work we cannot calculate. Displacement vector and all is not given, and time is also not given. So that part we cannot do. So we have to go with power is force dot velocity, right? So how to get the velocity? This is our prime objective. So force vector is already given. If we divide that by mass, so I will get the acceleration vector, right? Divide that by 2, which is mass. So it is 3t I cap and 3t square j cap, right? And once you know the acceleration, you can simply integrate it and get the value of velocity, right? Integrate it with respect to time. So integration of a dt is velocity, and everything here is going to be in vector format as well. So here we have integrated 3t square by 2 I cap plus 3t cube by 3 j cap. I believe the idea is very clear, right? Okay, so just integrate it and you have it 3t square by 2 and 3t cube by 3, right? 3t square by 2 and 3t cube by 3, no problem with that. Okay, all right. So once you have the velocity vector and the force vector with you, you can take the dot product of these two and get the value of instantaneous power. To get the dot product, what you need to do is whatever coefficient of I you have, the coefficient of IO you have over here, just multiply that 6t into 3t square by 2 plus 6t square force vector, and this is the velocity vector, so 3 and 3 can be cancelled out. So t cube. You just multiply it and you will have your final answer. So here you have it 9t cube plus 6t to the power 5, right? Option number D, right? Option number D is the correct option, which is clear, right? I believe the idea is very clear. Now efficiency is a very simple thing, right? Whenever you are performing some work on a system, or whenever you are investing some energy into the system, right? The system is supposed to perform some work, right? Let's say that you are investing thermal energy into the system, right? You are burning coal and you want the engine to work, right? So engine is doing a work of, let's say, 200 joules, but you are burning a coal of 2000 joules. So efficiency of engine is 200 upon 2000 into 100, right? So efficiency is output energy upon input energy into 100. Okay. Sometimes we make a machine, that means we invest energy by chemical, thermal, electrical, anyway, and we want mechanical work out of it, right? So in that case, efficiency will be output work upon input energy into 100. I believe the idea is very clear. Now, the next idea is the idea of motion in a vertical circle. Let's have a look at that part as well, right? So motion in a vertical circle. Very quick idea, we will talk about that. So motion in a vertical circle and collision, these topics are there, but they are not as important as the previous topics. So that's why we have invested so much time on the previous topics, and these topics we can do very easily as well. Let's do that and talk about the motion in a vertical circle. Okay, so here we have it, motion in a vertical circle. Just a second, here we have it, this one. So here, this is a ball, or we can call it, this is a bob on a particle, right? And it's a rope. So if the motion is happening like this is a motion in a vertical circle, my dear kids. During the journey of this particle along the circular path, the tension in the rope does not remain same, right? The tension in the rope does not remain same, it changes. And here, the governing forces, when the body is moving on a circular path like this, there are two governing forces. First is the tension force in the string, and second is the weight, right? These two forces are used to calculate everything in this situation. My dear kids, here we have a body and that is acted upon by two forces. So very clearly we can calculate very easily. We can deal with so many forces together. Here we have to deal with only two forces. Very easily we can do that. Here, this is the original position of the particle. At time t, when the particle is moving on a circular path, at time t, when the particle is here, the angle made from the initial position is theta, right? we will look at this position. At this position, what is happening? At this position, what is happening? Right, look at that. When the particle is moving like this, so at this position, the weight of the particle is acting downward. The weight is acting downward. And the tension in the string is along the string, of course, right? So these two are the governing forces, and by simplifying it, we can calculate everything at all, right? Now, we are interested in different places, what is the velocity or the instantaneous velocity of this ball or a particle, and how much tension is generated in the string in different places in the journey, right? Let's look at that for different positions. So here, for this specific place, the weight is acting downward. So we can say mg can have two components. This angle is theta. So this is also theta. So mg cos theta and mg sin theta. Here the tension is balanced by mg cos theta, right? And mg sin theta is providing you the restoring force. Okay, clear? Now let's look at that. Over here, because the entire motion is happening under gravity, you see, when the whole motion is happening in the motion in a vertical circle is happening in the gravity. So what is happening? When the body is rising, so here the potential energy is increasing. Think about it. The potential energy can also increase along this path. The potential energy can also increase along this path, right? Doesn't affect anything because potential energy, the gravitational force here is there in both the cases, and work done by the gravity is independent of the path taken because it's a conservative force, right? So the change of energy you are going to observe in this path or this path will be same, right? So that's what we are observing. The whole motion in a vertical circle is happening in a conservative field, which is why the mechanical energy will remain conserved, and which is why initial mechanical energy will remain same as the final mechanical energy as it moves ahead, right? So during this motion, initial point A and at a random time t, the particle is at point P. During this part, what happens? The mechanical energy will remain conserved because the particle is moving in a conservative field. So mechanical energy is same at both A and P. What is the mechanical energy at A? Because you started moving the particle with the initial velocity u. So there is, let's say this is the reference, this is the reference. So with respect to this reference, there is no potential energy, right? So all the energy is half mu square, kinetic energy. As it rises at point P, it has risen by this much height, right? So it has acquired some potential energy, and it has also a velocity v, right? So the total mechanical energy over here is mgh plus half mv square, right? mgh plus half mv square. How will you get the value of velocity over here? So the velocity you can calculate very easily. How can you calculate the value of velocity over here? So by doing so first of all, how can you get the value of h? We can say the total, this thing is the radius of the circle r, right? And this thing, this is when the rope is over here, this is also r. This thing will be r cos theta, right? This is theta, so this is r cos theta. So what is h over here? R minus r cos theta. So r1 minus cos theta. R minus r cos theta, r1 minus cos theta. So r1 minus cos theta is written over here. This is h. Look at this, this is h, okay? r1 minus cos theta. So just put the values over here and you can get the value of velocity at this particular point, right? Okay. You can get the value of velocity over here. So from here you can get that. My dear kids, as you know that if anything wants to rotate in a circular path, we need a force that should act towards the center, or we have to provide the necessary centripetal force, right? We have to provide the necessary centripetal force, otherwise the body will not move in a circular path, right? So as long as the body is moving in a circular path, the effect of all the forces should be such that they provide the required centripetal force. My dear kids, let's stop the body at a random point and see what are the net forces acting on the body that is providing the centripetal force. Centripetal force is along the center, right? Along this way, right? So along this way we have tension and a component of weight, mg cos theta, mg cos theta, right? So you see that T minus mg cos theta, T minus mg cos theta, this is the net force that should act towards the center, T minus mg cos theta, and that net force should provide you the required centripetal force mv square by r, right? This is the force calculation, right? This is the force calculation. Previously we had done the energy calculation, right? So in the first step of motion in a circle, you said that potential energy, mechanical energy should remain same because it is moving in a conservative force field, right? And here you have seen when you try to balance the forces, we have T minus mg cos theta is mv square by r, right? So you can easily calculate these parts as well. I believe the idea is very, very clear, right? So at a random location theta, the value of velocity of a particle over here can be written in terms of theta, right? At a random location theta, the centripetal force or the tension in the rope can be written like this. So from this, tension in the rope can be written like this, okay? So you have two expressions. From the first calculation of energy, you have calculated velocity at a random point when the angle was theta, and by the calculating the forces, you have understood what is the tension in the rope when the angle is theta at a random location, right? So you have expression for tension, you have expression for velocity for a time t, right? These two expressions are there. Now for different locations, we can calculate velocity and time without any problem. My dear kids, this is the original position when the angle is 0, right? You just launch it with initial velocity u, right? So put the theta 0 and solve it, you will find this term will come out to be 0, and the initial velocity, the velocity at this point of the body comes out to be initial velocity at which you have launched it, u, right? So when theta is 0, velocity is only u. Tension in the rope, how much tension in the rope should be there? How much tension in the rope should be there so that the body can stay in the circular path? So you see that just put theta 0, so cos 0 is 1, so it is mg plus mv square by r. Mg plus mv square by r, v is velocity over here is u, so mg plus mu square by r is the value of tension over here. Now similarly, look at this condition. When the theta is 90, so when the theta is 90 over here, you see that this is the very critical point, very crucial point to cross. Otherwise, the body, if the body does not have enough velocity at this point, it will not be able to cross it. Yes or no? It will fall like this. Yes or no? It will fall like this. You see? If the body is not able to cross it, it will fall like this. So you see, I am trying to launch it with a certain velocity. You see, it will come back and it will perform oscillatory motion, right? You see that again, the velocity was not enough to cross this point, right? Again, I launch with it crossed it, right? But you see that velocity was just enough to cross this point, but not really enough to cross the topmost point. So what happened? It crossed this point, then it fell back in a very specific way. You see? You see? Now it crossed it, right? So you see that every point has a very specific criteria so that you can cross that particular point. So here it is. When you put theta is equals to 90 over here, the velocity at this point B will come out to be root v u square minus 2gr, and the tension in the rope will come out to be this much, right? And similarly for theta is 180. When theta is 180, this is a very critical point, point C, right? So if the velocity, this is the velocity at that point, and that is the tension at that point, very, very important, mu square by r minus 5 mg, right? Okay, my dear kids, if you are launching the body with the initial velocity u, right? So what should be the velocity at this point, or what is the condition for the body to just complete the circle, my dear kids? If the body wants to complete a circular path, at no point the tension in the rope should be, the rope must not slack, right? The rope must not slack. So we see that at topmost point, if the rope is like this, the body cannot move ahead. It will not complete the circle, right? So rope must not slack. The rope must remain straight like this, right? And the minimum value of tension you can have in that situation is 0 or more than 0, right? So to just cross it, if you want the rope to remain stretched, so the tension on the rope should be greater or equals to 0, right? So that for the critical condition, this should be 0. So mu square by r minus 5 mg, mu square by r minus 5 mg is 0 for critical, for just crossing this point and just completing the circle. So mu square by r is equals to 5 mg, m and m is cancelled, u square is 5g, or r you can take it on this side. So u equals to under root 5 gr. Right. So you must launch the body at this velocity root 5 gr so that it had enough kinetic energy so that it can cross the point C, right? If you are launching the body, initial velocity is root 5 gr, then it will cross the point C, and if it is less than that, then it will not, right? So if it is more than that, then it will definitely cross it, right? So yeah, the angle is 270. Clearly you can calculate for rest of the angles as well. So yeah, so for all 4 points you have calculated, for angle D it is 270. For all 4 points you have this table, right, and you can have it. Okay. So this is the velocity you need to have, you need to launch the body at, right, so that it can complete the circle, root 5 gr. So the velocity launching velocity is more than that, the body will definitely complete the circle, and the tension in the string will never be 0, right, the string will never slack. If it is root 5 gr, if it is equals to that, then the tension at the highest point is going to be 0, but it will just complete the circle, right? And if it is in between root 2 gr to root 5 gr, root 2 gr is the velocity required at this point. You see that root 2 gr is the velocity required at point B. You see, if you just solve it for this expression, this thing becomes 0, right? If the rope comes over here at point B, at this point when theta is 90 degree, when theta is 90 degree, tension in the rope is this much, right? If at point B the tension becomes 0, then what will happen? If at point B the tension becomes 0, then what will happen? Just put it, solve it. This expression you can do 0, so u will become under root 2 gr, right? So just think about it. If you have to launch with at least root 2 gr so that it can reach at this point, right? So when you are launching it at root 2 gr, the body reaches at point B and it will not cross it, okay? So what is happening over here? So if the velocity is higher than root 2 gr, so it will cross point B, but it is less than root 5 gr, it will not cross the topmost point. So what will happen? Particle will not follow the circular motion. Tension in the string will become 0 somewhere between B and C. Somewhere between B and C. Here you have B, here you have C, right? So in between this journey, here velocity you need to cross this point is root 2 gr. Velocity you need to cross this point, the topmost point is root 5 gr, right? So if the velocity is the launching velocity is between root 2 gr and root 5 gr, then what is going to happen? We can say that the body will not cross point C, it will just cross point B. It will somewhere here, the body will fall back, right? And it will follow a parabolic path. Okay. Now after that you have this part. If it is at root 2 gr, as I have already told you, it will reach the point B and it will come back, right? So if it is less than root 2 gr, then it will not even reach to point B, right? Clear? So all these things, the motion in a vertical circle can be explained, or the numerical or the questions that the NEET may ask can be answered if you have understood the theory in a very clear way. So just look at these whatever explanation I gave you, right? And just start with a blank paper and do these two things, right? First, do the mechanical energy conservation, right? And you will get one equation of velocity. Do the conservation, and then in the second part, you have to talk about the forces. So do the force balancing and talk about the tension force, right? So if you have expression for velocity at an angle theta, expression for force at angle theta, you can calculate any other thing, right? So these are all the parameters that you have, right? Okay. So once you know the value of velocity at every point, you can get the value of energy at every other point as well. So you know that value of velocity at A, B, C, you can calculate very easily, right, by the expression of velocity, right? In this list you have it. In this list you have it. value of velocity at different points you have. Once you know the mass of the particle is m and the value of velocity you know already, you can just calculate the value of kinetic energy very easily at every other point. Okay. Now look at this question and try to solve it. A particle is projected so as to just move along a vertical circle of radius r. The ratio of tension in the string when the particle is at the lowest and the highest point on the circle is. So basically, very easy question, right? We want it to just complete the circles. You see that the ratio of the tension in the string when the particle is at the lowest and highest point of the circle, a particle is projected so that it is, we just want it to complete the circle, right? So as to just move along a vertical circle. This just moving along a vertical circle is telling us that the top, we are just launching it with root 5 gr velocity, right? So at the topmost point, the tension becomes 0 because the particle is just completing the circle. That means tension at the topmost point is 0. Tension at the topmost point is 0. We have to talk about the tension at the lowest point and the tension at the highest point, the ratio of that. My dear kids, we will have some tension at the lowest point in that case situation, lowest point, and tension at the topmost point. My dear kids, since that part is 0, anything upon 0 is infinity, undefined, right? So answer should be undefined. We don't have to worry about the tension at the lowest point at all. A stone of mass m tied to a string is being whirled in a vertical circle with a uniform speed. The tension in the string is going to be the same throughout the motion? No, it does not remain same throughout the motion. Minimum at the highest position of a circular path? Yes, it is true. Minimum at the lowest position? No. Minimum when the rope is in the horizontal position? No. So option B is correct in this particular situation. All right. So that's pretty much everything about the idea of motion in a vertical circle. I believe the key ideas are very, very clear to you and you can answer the questions asked in the NEET exams for the motion in a vertical circle. Now you have some idea about the collision as well. Now, in the previous years, you will not find many questions on the collision, but if you have the key ideas clear with you, you can form equations very easily and solve the questions by yourself, right? That's it. So let's have a look at the last part, which is collision, right? So let's have a look at that. So here we have it. In the collision, what happens when we have two particles that are trying to collide, one and the second one? All right. When we have two particles that are trying to collide, what will happen? Here, just to show you, I am moving the particles. So I am doing the work and these particles are moving and performing. But think about it. On a plane, you have to imagine not anyone moving the particle. On a plane, these two things are moving with their own energies. So this one is moving with a kinetic energy K1. This one is moving with kinetic energy K2. I am not providing energy. I am not doing this. So what will happen? The first particle is moving with a certain kinetic energy on its own and the second particle is moving with certain kinetic energy and then they are colliding, right? My dear kids, over here, a new kind of system will come into the picture that is called as isolated system. Understand that? What is isolated system? Isolated system. A system on which there are no external forces is called as isolated system, right? So here, if these two particles are colliding, the collision is not happening because I wanted it. They already had the kinetic energies initially and by using their own kinetic energy, this collision is happening, not by my interference, right? So here, the external force on the system, is 0. My dear kids, if the external force on the system is 0 and by the Newton's second law, you know that force equals to rate of change of momentum. If force is 0, that means rate of change of momentum is 0 or the momentum will remain constant, it will not change. Okay? Momentum will not change. You see that? The force on system is 0, so momentum of the system will remain constant. Listen it one more time. During the collision is happening because of particles' own kinetic energy and no forces are applied on the system. No forces are applied on the system. This particle will apply force on this one, this will apply force on this one, but on the system you are not applying any force. Because the system is not experiencing any force, so system will not experience any change in the momentum, right? That means before collision, whatever total momentum was there in the system, after collision, the same momentum will remain in the system as well. I believe that is very, very clear. Okay. So, let's move on and talk about how to apply it. Now, types of collision, we can describe it. There are different types of collision that can happen, right? The first is elastic collision. In the elastic collision, what will happen? Particles will not lose their energies at all, right? Particles will not lose their energy at all. So, what will happen? The total kinetic energy before and after the collision remains same. So, what will happen? Particles are not losing their energies at all. So, total kinetic energy of the system remains same. Or when it is happening on the ground, so it will strike the ground and it will bounce back to the same level if it is the elastic collision, right? In the inelastic collision, what happens? However, some deformations take into the picture, or we can say a part of the energy of the system waste to deform. Think about it. If I take a can, or if I take a cardboard box, right, a box made of cardboard, right, and I throw it hard on the surface, on the ground, what will happen? It will bounce back by a certain height, but that cardboard will be deformed as well. Now think about it. If you lift a cardboard and I try to deform it, it will take some energy, right? And now by throwing it, it is deformed, means some of the energy that you had provided is wasted to deform it. Yes or no? So clearly, in that situation, if the collision is inelastic, the kinetic energy does not remain same. Total energies are conserved. A part of the energy was wasted in deformation. Here in the elastic collision, no permanent deformation takes into the picture, which is why the kinetic energy remains same. In the inelastic collision, because there are deformations taking into the picture, so part of the energy is wasted in deforming it. So clearly, we can say the kinetic energy will not remain same. In perfectly inelastic, that means you can take a clay, right, a piece of clay, and you throw it, right. So what happens? The clay will simply go ahead and stick to the ground, right. So what will that do is, whatever shape of clay you had in your hand, if it was spherical, it will entirely change and it will stick to the ground. It will not bounce even a bit. So all of the energy you provided is wasted to deform it, right? And that's how the inelastic collision is happening. When there is inelastic collision, when the collision is inelastic, then the particle will get it stuck together after the collision, right? That is perfectly inelastic collision, right? So yeah. And here the loss of kinetic energy is maximum. Okay. Okay. So perfectly inelastic collision. So you see that lot of deformation is happening, right? Inelastic collision. So it will bounce back, but not to the same height. And in the elastic collision, it is bouncing back to the same height. Yeah. On the basis of direction, the types of collision can be described in this way, right? You can have one-dimensional collision or head-on collision, or you can also have two-dimensional collision or oblique collision, right? What is the difference between them? Very simple. In the one-dimensional collision, what will happen? The bodies before and after collision will follow the same line of action, right? In the oblique collision, however, what will happen? Before collision and after collision, the plane will not remain same, right? As you may have seen while playing the carom, right? Sometimes the striker hits the carom coin at an angle, right? This is the striker. It hits the carom coin, let's say in the side. So what will happen? The striker will follow this path and the coin will go that way. So this is happening in two dimension, right? If you are hitting the carom coin like this, head on, so what will happen? The coin might go this way and the striker might go this way after collision. So this is one-dimensional collision. So what will happen? A collision in which the particles move along the same straight line before and after collision, it is defined as one-dimensional collision. But a collision in which particles move in a different plane at a different angles before and after, it is oblique collision. right? I'll show you a question of the oblique collision and it will clear every doubt by default, right? Let's have a look at that. So this is the coefficient of restitution we are willing to understand. Newton performed various experiments by colliding different particles of different material, and for a particular set of material, colliding material, he calculated a ratio, right, by looking at the velocities at which they were coming and the velocities at which they are leaving out, right? He found out there is always a ratio, and that ratio is always a constant. Doesn't matter how fast those two particles are moving and how slow these particles are moving, right? For a pair of particles, that coefficient of restitution came out to be constant, right? So over here you see that these two particles are colliding, right? This is when the impact just starts. So what will happen? Due to the impact, their deformation will happen and then they will bounce back, right? So when the bouncing back is happening, so restitution is happening in that time. So the coefficient of restitution is velocity of separation upon velocity of approach. This is the ratio. So velocity of separation, by what velocity they are separating? So if after collision the velocities are v1, v2, before collision the velocities were u1, u2, so velocity of separation will be v2 minus v1, right? And because if it has to approach, think about it, if the particles are moving in this way, both the particles are moving in this way, and we want the collision to happen, if the particle ahead is moving faster and the particle behind is moving slower, the collision will never happen, right? Collision can only happen if the particle behind is faster, right? Okay. So right now velocity of approach is u1 minus u2, right? And they can only move apart if one particle, maybe the second particle is moving faster than the first particle, right? So u2, v2 is more than v1, right? So velocity of separation is v2 minus v1 upon u1 minus u2. So that's it. So for the elastic collision, E is 1. We found out this ratio is 1. For inelastic collision, the ratio coefficient of restitution is between 0 to 1. And for perfectly inelastic collision, it is 0. For a NEET syllabus, the questions are asked in the nature of elastic collision, right? So the questions are going to be very, very easy. You just have to do the momentum conservation, right? And you can solve it, right? Okay. Now, let's have a look at a numerical on this part, right? So as I have already told you, we are going to talk about the collision in one dimension only in the NEET, for the NEET perspective, right? And we are only going to limit ourselves to the elastic collision, right? We will not go into the inelastic collision for the NEET. Okay, so what is happening? Look at this thing. There were two bodies. They were initially moving with 5 meters per second and 3 meters per second in the same direction, right? After collision, one particle starts moving with 4 meters per second. What will be the velocity of the first particle, given the mass of these bodies is 2 kilogram and 1 kilogram? Okay, listen it one more time, right? These two bodies are there, right? 5 if the first one was moving with 5, the second was moving with 3 in the same direction, they collide. Because the previous one was moving much faster, it will collide into this one, right? After the collision, the second body starts moving with 4 meters per second. We have to talk about what is the velocity of this particle, right? So let's understand that. So here, as I said, if you look at the system, the collision is happening because of particles' its own kinetic energy. We are not providing any other external force. So for the system, the momentum will remain same. So momentum of the system before collision, it is m1 u1 plus m2 u2. That should remain same as momentum of the system after collision, m1 v1 plus m2 v2. My dear kids, here all the values are given, right? Just put it 2, 5, 1, 3. Here 2, let's say velocity of the first particle after collision is v1. This is what we have to calculate, okay? And similarly 4 and 1. Just put the values, and by solving it you can calculate it, what will be the value of v1, That's a very simple idea, right? That's pretty much everything about this particular thing, right? And so far what we have done, my dear kids, we have talked about work done, the concept of work done. We have also talked about the concept of work done by constant forces and variable forces. We have also discussed in detail, in a very detailed manner, a concept of energy and work energy theorem. After that, after talking about all that, we have also talked about concept of power, and we have seen it different types of energies as well, right? We have understood the meaning of conservative forces and non-conservative forces, right? And we have seen the idea of potential energy is limited to the conservative force fields, right? After that, we talked about some idea of motion in a vertical circle. We looked at the tension in the rope and the velocities at different points in the vertical circle. These two things are there, right? And after that, we talked about the collision in one dimension, or elastic collision in one dimension, right? We understood that the kinetic energies in the in this particular situation will remain same, right? Before and after collision in the elastic collisions, and also the momentum will remain conserved. My dear kids, momentum will remain conserved irrespective of the type of collision, right? Now, on this note, I believe every concept is crystal clear to you. I have shared, my dear kids, now some DPP with you, right? In that DPP, you will find a lot of questions for you to practice. You can just go ahead through the link given in the description and practice those questions, right? If you practice those questions after this class, you will find that every concept becomes crystal clear to you, and you will become very, very confident, right, for this particular chapter, right? So on this note, let us close this class over here only, right? And I'll see you there in the next class. Till then, take care. Bye-bye.